Welcome to this explainer. For generations, we've basically assumed that taller means healthier. We associate physical height with vitality and evolutionary fitness. But when we actually dig strictly into the clinical and demographic data, a really fascinating biological paradox emerges. Our overarching thesis today is this: smaller human bodies inherently endure less biological entropy, and because of this, they possess a greater statistical potential for extreme longevity. This is absolutely crucial because it directly challenges the misconception that bigger is always biologically better, a bias that heavily affects how we view our own health and physiological development.
It's a completely counterintuitive concept, right? But the data is robust. Today, we're exploring this across 5 distinct areas. We'll start with the stature longevity paradox, explore our evolutionary origins, detail the physiological costs of size, examine massive demographic lifespan datasets, and finally, look at stature decline and aging as a critical clinical indicator.
Let's jump right into Section 1, the stature longevity paradox. Using the SAMARA's review data, this section establishes a really fascinating reality. It shows us that while taller individuals might enjoy certain socioeconomic advantages in society, shorter bodies actually suffer fewer age-related chronic diseases. They are significantly more likely to reach advanced ages. So it fundamentally separates social privilege from actual biological efficiency.
To understand why this happens, we have to look at biological entropy. Think of it as the gradual, inevitable decline of an organism's physiological functions. The cellular mathematics here are pretty straightforward. Larger frames inherently have higher total cell counts. More cells mean a higher baseline requirement for cell division. And over decades, this mathematically increases the baseline rate of DNA replication errors. It accelerates the accumulation of cellular damage and essentially moves the organism closer to systemic failure.
Okay, Section 2, evolutionary origins of height. To really grasp the modern human frame, I'm incredibly curious about our genetic origins. Where did this drive for larger, more robust bodies actually come from? And what were the original evolutionary trade-offs?
This historical comparison actually flips the script on what we often assume. There's this common myth that Neanderthals were short and squat. In reality, they were incredibly robust, with thick bones and heavy muscle mass, adapted specifically for cold climates. Early Homo sapiens, our primary genetic baseline, were typically more gracile. That means they had a thinner, smaller, and highly efficient frame, which is associated with longevity markers like the FOXO3 gene. So, when early humans interbred with Neanderthals, specific alleles introduced unprecedented skeletal heaviness and density into modern European lineages.
Exactly. And this biological exchange is what we call introgression. It's the transfer of genetic information from one species to another through hybridization. Now, while these newly acquired robust variants provided clear survival advantages in harsh, cold climates, essentially acting as a sort of hybrid vigor toolkit, they came with a biological cost. They shifted modern humans away from that highly efficient gracile longevity baseline, imposing higher caloric needs and far greater long-term metabolic stress on the body.
Which brings us perfectly to Section 3, physiological costs of size. We need to pivot away from the distant past and look at the actual physiological and metabolic mechanics that tax larger human bodies on a cellular level today.
When we look at the demographic data mapping out the 100% longevity potential baseline, notice the precise statistical drop-off. For individuals ranging up to 5 foot 4 inches, they maintain a 100% longevity potential. They have a mean age at death of 84 years and maximum mobility retention. But the moment a human frame surpasses 5 foot 4 inches, that efficiency drops. At 5 foot 5 inches, potential drops to 95%. By 5 foot 6 inches, it drops to 90%, and the mean age at death statistically lowers to 82 years. The mechanical advantage of shorter limbs and lower joint compression simply wanes as the overall frame expands.
Let's meticulously break down the biological advantages inherent to a shorter stature. First, we see reduced cellular replication requirements. Second, a proportional lowering of total DNA damage over time. Third, higher levels of sex hormone-binding globulin. Fourth, lower insulin-like growth factor 1, or IGF-1, which is strongly linked to reduced cancer incidence. And fifth, a significantly reduced cardiac pressure gradient. That simply means there's a shorter distance the heart must pump blood against gravity, which statistically delays cardiovascular aging.
That is absolutely fascinating. So, the crucial point is how this cellular reality translates to actual massive populations. Section 4 covers demographic lifespan data.
To prove this isn't just theoretical, we're referencing an enormous cohort study from Poland. It tracks all adult deaths between 2004 and 2008, analyzing over 845,000 individuals. Tracking these historical cohorts from Poland, you can clearly see the distinct inverse relationship between adult stature and lifespan. This specific data tracks individuals born between 1896 and 1925. For the men in the very short category, they consistently hit the highest mean age at death. Meanwhile, the tall and very tall categories experienced a sharp, undeniable downward trajectory in overall lifespan.
And just to verify that this isn't an anomaly of early 20th century hardships, we examine the cohorts born between 1946 and 1965. The inverse correlation holds remarkably true across multiple generational cohorts. While there are slight variations for women based on specific birth years, the trend for men remains rigidly linear. These shortest males consistently exhibit the highest mean age at death. The fundamental biological rule is striking here. Smaller frames outlast larger ones over the grand scale of demographic time.
This leads us to our final analytical section, stature decline and aging. We have to shift our focus from static peak height to dynamic changes. Specifically, we're looking at the gerontological indicator of height decline over time. We want to know what happens to the skeleton as we reach late ontogeny or the late stages of life.
Which poses a critical clinical question. We all know people tend to shrink a little bit as they age, but what does rapid stature decline in these late stages of life actually indicate about an individual's systemic aging profile? Is it just a harmless cosmetic change, or is it a warning siren of deeper biological failure?
It is very much a warning siren. Looking at the Polish longitudinal study on aging, pay attention to the data representing individuals losing 3 centimeters or more per decade. That rate of rapid height loss is directly correlated with severe spikes in cardiovascular disease and all-cause mortality. It isn't just a shrinking spine, it functions as a highly reliable metric of rapid systemic deterioration.
The clinical risks associated with this stature decline are severe. A loss of 3 centimeters or more per decade signals the osteoporotic collapse of the vertebrae. And this collapse triggers a cascade of heavy consequences. We see an independently heightened risk of cardiovascular disease, a drastically increased incidence of musculoskeletal disorders, and severe physical frailty leading to hypokinesia, which simply means decreased bodily movement. The structural collapse of the frame directly accelerates the failure of the biological systems housed within it.
To summarize, as researchers have noted, adult stature is incredibly informative. It reflects our early nutritional status, but it also dictates the mechanical and cellular boundaries of our mortality, morbidity, and life expectancy. The aging process is certainly somewhat malleable based on our lifestyle choices, but the empirical data we've reviewed thoroughly refutes the long-standing societal assumption we all grew up with, that larger human frames are inherently biologically superior. Actually, quite the opposite is true.
Which leaves us with a final, provocative thought to conclude this explainer. If smaller human frames inherently possess lower biological entropy, experience less cellular damage, and clearly demonstrate greater longevity potential, we really have to ask ourselves, how should we reevaluate modern nutritional and public health goals? Our current paradigms often implicitly promote continued secular growth, prioritizing maximum physical size. Perhaps it's time we shift our focus away from maximizing growth and instead prioritize optimal long-term cellular efficiency.